Okay, so you pretty much gonna know what it's about because that's the practical implementation. So please welcome Andreas Vogt.
Yeah, thank you. I must apologize in advance. Defense is not sexy, it's not as nice as all the other talks about breaking things. It's boring, it's math, and well, if you enjoy it anyways, you're very welcome. So, certified programming with dependent types. I think most of my talk will be an introduction into what exactly dependent types are, because I think many people do not know. If you know Haskell, you can skip the first half of the talk and come back later. If you have experience with Cork, you can come back 5 minutes before the end. And for everybody else, which I assume is the majority in that room, I'm going through the motions very, very slowly. I've liberally stolen examples from the excellent book by Benjamin Pierce and colleagues. It's called Software Foundations. It diverts off on the way towards formal verification and program language semantics that I'm not going to deal with. I'm just using enough out of that to explain how data and proofs work in Coq, and then show how dependent types work in Coq and what you can do with it. I'd especially like to thank Marco Schilpe. He's the guy who wrote the software with me, and he's a brilliant mathematician, still learning how to write big applications, and for me it's the other way around. So we extend each other magnificently. What you see here is an Emacs running Proof General, and that's an interactive connection to Coq. Coq COQ is a so-called proof assistant. I can interactively execute statements here, and then they're highlighted blue in the top window, and in the bottom window you see the output we're getting. So that's comments. Okay, I'm going to start with the TLDR if you know everything else about Haskell and types. Dependent types are types that do reference back on code. So, for instance, you can talk about properties of some type of data. And in regular language, you can say x is an integer, well, the type is obviously integer. If you have dependent types, you can say x is an integer and x is even, or x is an integer and x is prime, or that list is sorted. So you can use arbitrary propositions that make up the type. So it consists of a base type and consists of a proposition that's true for every element of the type. And you can do funky stuff with it, like making sure that if your function depends on some precondition, that the caller has to prove he meets the precondition, or that you can tell in your software that what you return is not just a list, but a sorted list. So that's a TLDR. And now for really starting with 0. So Coq, the tool I'm using, is a French proof assistant. It's written by a subset of the people that also did the OCaml stuff. It uses the calculus of inductive constructions for data types. It uses the lambda calculus for calculations. And it bootstraps everything else, the whole computational universe, as well as the whole mathematical universe out of that. Okay, I'm going to start with lambda calculus because that's something many people faintly remember. So most of the people who did computer science undergrad studies once heard about the Turing machine, and then they heard that the lambda calculus is equivalent to the Turing machine, not much more about it, which is a shame because, yes, it's computationally equivalent, but the proofs are 20 times easier than doing proofs in a Turing machine. So if you want to write certified software, meaning software where you can prove that it fulfills a certain property, it really helps if the proofs are kept short. So using the right mathematical foundation is important to make sure that the whole process is viable from an engineering point of view. You want to end up with a software and you want to end up with a proof. You want both to be manageable. Lambda calculus consists, well, colloquially speaking, if you say f of x, and normal mathematical notation. Equals x times x. Then we know if we want to calculate f of 3, we take the x and substitute it by 3. So lambda calculus is essentially function definition, function application, and using substitution for that. Like that, right? That intuitively is lambda calculus. You define functions, they have parameter is substituted, end of story. Now for the calculus of inductive constructions. So lambda calculus works on some x's where things are in there that get substituted, and the logical question is what things? You have to be able to talk about the data you're computing on. That's where the calculus of inductive constructions comes into play, because it, as the name says, allows inductive definitions of new types. And with Coq, we're really starting in a vacuum. Nothing exists. Okay, you get a standard library, but I explain to you how central concepts are implemented in that standard library, so you get an idea of how programming that works. I open a temporary module to hide the standard definition library because we're going to start to define Booleans. Inductive is the keyword. It says we are defining an inductive definition here that gives the name, bool. It's a set. We are defining a set bool. And we're giving two constructors here. One is called true, one is called false. And both constructors have the type bool. That means they're taking no arguments. I can do that definition. See, bool is defined. A couple of other stuff is defined that gets interesting later. I can use the check command to see the type of an expression. So I can write true, and if I say check true, I see colon bool. We are dealing with bool here. Same, of course, for false. Check only looks at the type of an expression if I want to actually evaluate an expression, compute the result of an expression to use eval. That's what I'm doing here. Okay, so yeah, we still need one other bit of the puzzle to finish being able to write anything we need, and that's writing functions. As I said, it's based on lambda calculus, so if I pass a b here, it gets substituted there. And the only thing that is added to the language beyond that is that match construct. You give it an expression here, and then you have a breakdown of possible values there, and then the results. If you have ever written Haskell or OCaml or something like that, that's totally obvious to you. The interesting difference towards Haskell and ML is that all functions are total, meaning it's defined for the whole range of arguments. And in such a match, every possible constructive type must be defined. So I cannot leave away the false branch in the match here. It always has to be complete. So if I look at that bool not, that of course also has a type. And the type in this case is bool, arrow, bool. So in other words, a function that takes a bool and returns a bool. I can also take the type of an application of that function. So if I pass true to bool not, that's an expression that has also type bool. So type was bool, arrow, bool. I pass a bool, and bool remains. And of course, I can compute the values. Bool not from false is true. Bool not from true is false. I think that should be pretty obvious until there. There's a third way to actually do something like computations, and that is the example facility, which in fact states a theorem, and you can also use a theorem or lemma keyword, that doesn't matter, but I'm using an example here because I use it as an example. I say my test bool not of true equals false, and then that happens. I see, that's the interactive proof editing mode of Coq, the proof assistant mode. What I'm seeing here, below that double dashed line is the goal I want to prove. And above that is the hypothesis I have. At the moment, I do not have any. What I can do is simplify the expression, which applies the function essentially, Then using reflexivity as a, you talk about tactics, small tactics that get you closer to the proof. And reflexivity says something is true if both sides of the equal sign are equal. So I say that. And I said proof completed, and I can say QD. Yeah, I've shown that the example is always correct. Good. We will see more about that proof facility later and about how proofs are implemented, because that's really fascinating. That's where your mind starts blowing. That's the boring stuff, but I will tell that so you get the rest. That's another definition. This time we pass two variables. So again, definition, the keyword for the definition, name of the function. Parameter b1 is a bool, parameter b2 is a bool. The type of the definition, again, is bool. And the result type. And there again is a match that implements Boolean OR. I can check that, and again, the type is bool, arrow, bool, arrow, bool, which means I have to pass two Booleans to get out another Boolean. Or if I pass in one Boolean, it's also something people in static type languages are familiar with. If I pass in one Boolean, I'm getting back another function that takes a next Boolean and then returns a Boolean. Of course, I can evaluate that. I can check. So, okay, here's the case. If I pass two arguments, I can evaluate that, get back a result. Okay, now stuff is getting more interesting because we have Booleans. Now we define natural numbers. Again, it's an inductive data type. And the peculiar thing about inductive data types is that it gives us a lot of information that we will need later when doing proofs for that code. Because in such an inductive definition, I know if I have an instance of a nut, of a natural number, I know that it had been either constructed using this constructor or that constructor. In that case, this looks like the definition of true in the Boolean. We have a constructor that's called O, and it directly returns an instance of nut. And then I have another constructor. Could you turn that off, please? We have another constructor, S, for successor, and that constructor has a type nut, arrow, nut. So it's a function that takes a nut and returns a nut. That means there are two ways to construct a nut. Either I say O, and I call it my zero, or I can say successor of another number. Like O is a number, C, type nut here. Successor of O is a number. I could call that 1. The successor of O is also a number. You could call that 2. And in fact, we do see that a bit. And again, I can define functions working on that. That's the predecessor function. And I have a match here. I'm cheating because my function is total, so the predecessor of 0 is also 0. But for the other case, the n I pass here is destructed. I know it's the other case, it's not O, because O is that case. So there must have been an n prime that was used to generate my n. So matching with s n prime destructs the s n prime and can use the n prime on the right-hand side. So I pass a 1 here, which is s of 0. The n prime matches with a 0. I end up with a 0 and return a 0 here. And again, I can test that by computing the predecessor of 2. That is 1. Okay, I'm leaving my own world for a bit, go back to the standard library, because all that I've shown you is part of the standard library. And in fact, ordinary numbers, like the 4, are just syntactic sugar for successor of successor of successor of successor of 0. That's also 4. And I can compute successor of successor of successor of successor of 0. I'm getting 4. And I can compute successor of 4, getting 5. Okay. Natural numbers, yeah. Back to excursion mode, because we're defining more stuff that's in the standard library usually. Adding two numbers, now that's a little bit more difficult because we need to have a recursive call in there. And what we have to do here is do a fixed point definition. That's why we have the fixed point keyword here, not the definition keyword. So I'm passing, it's again a function definition, with the difference that the name is bound in the body of the functions and can call it here recursively. I pass it an n and an m. Again, returns the nut. And I think how it works is obvious. If n is 0, the result is m. If n is 1, it matches here. So it's the successor of n prime plus m, and that eventually terminates when n prime hits 0 and gets passed here. So if I pass 2 and 3, it calls plus with 1 and 4, and then with 0 and 5, and then it returns 5. That's a very interesting message, because actually coq is not Turing complete. I know you're all shocked. You cannot define a recursive function in coq without giving proof that it terminates. So it's not, we circumvent the halting problem by just not looking at the part of the problem space where we cannot come up with a proof for termination. So either you have a proof of termination or you cannot write the function. That makes stuff sometimes a bit harder. You sometimes find bugs you wouldn't otherwise. And most importantly, if you could have functions that do not terminate, you could have vacuous proofs of infinite size that prove everything that breaks the proof part of it. But that's the technical aspects. Okay, but anyways, what you see here is that in that match, we destruct the n. We're taking s n prime. And eventually, we match with a 0. And we have inductive definition, so the compiler knows that there are only 2 ways to generate a natural number. That's 0 and successor. And it sees that this argument, n, is structurally decreasing in every recursive call on its own. So it says, recursively defined, decreasing on first argument. Sometimes it's not that easy, and then you might have to work hard. In that case, it's easy. Okay, we can do the computation here. Now that is nifty. You can actually extend the grammar of the language by adding grammar production rules to it while writing your program. So x plus y, you can come up with a notation for that. You say this is equal to that. Just like that, come up with your own mathematical notation, which is extremely useful. So 2 plus 3 is still 5. And then, of course, you can implement multiplication recursively by calling plus all of the time. And, you know, I said we are starting in an empty universe. You're not even getting equality for free. Well, actually, in the latest versions, you do. There's some auxiliary function that generates it. But you also can, and sometimes you have, to define your own notion of equality. So BEQ nut, that's a Boolean equal for the type nut. That's why the funky name. But that essentially tests whether 2 numbers are the same by, you know, taking, using structural recursion until both sides are 0. If they are both 0, they're the same. If they're not both 0, they're not the same. Okay. Yeah, I need that function later, so I'm going to show it to you now. You can also match on nested expressions here. That's one of the main reasons. We have a function even b. It takes a nut, returns a Boolean. That's why the b. And we're matching on either 0, that's true, or 1, that's false, or if it's the successor of some number, where the number is not 0. It could be 0, right? It could be. It recursively calls itself. So now the funky part. You can take the code you have written like that and extract it into either Haskell code, which then looks like this, or you can extract it into OCaml code, which then looks like that. So the stuff I've been working on since the last talk is a PDF parser. I intended to write a PDF renderer, but turned out writing a PDF parser was enough of a problem. And the route we chose was actually writing the implementation in coq, then extracting that to OCaml, using that to compile the binary. So that's a viable way. Essentially, we're using Haskell and OCaml as assembler here because all of the interesting stuff that I'm coming to in a moment, like having proofs about your code and passing around proofs, that gets extracted away, and that's not part of the executional model. Okay, so I can write programs, I can extract them to OCaml and compile that. Wonderful. Now for the proof part. You can, there are, I mentioned so-called tactics. I'm going to look into a couple of standard tactics that you use to solve, to prove stuff. Just to give you a rough idea. I don't expect you to remember that or being able to actually use that, just to give you an idea of how that works. So I'm stating a theorem here. I'm giving that theorem a name, then a colon. And then here is the actual proposition I'm trying to prove. So I'm saying here for all n of type NOT, 0 plus n equals n. So that's our goal. The first tactic I use is called intros. That takes the for all from my proof goal and pulls it up into the assumptions. Then I can simplify the expressions, you have seen that before, and I can then use reflexivity, which you also have seen before, to show that it's true, QED. Actually, reflexivity calls simplification before, so I'm going to skip using reflexivity from now on. Okay, next example. I say if n equals m, then arrow's implication, n plus n equals m plus n. Which is kind of obvious, but unfortunately you have to prove even the obvious stuff. Or maybe fortunately, because you do not overlook stuff that you think is obviously correct when it isn't. So again, we're using, that's our proof goal. We're using intros to pull up the n and the m into the assumptions. We then use intros again to split up that implication, because that's an assumption if I want to show that. That's what the implication means. So I pull that up as well. And now I see I have an equality here, a hypothesis H, that n equals m. And I can use rewrite to actually rewrite the n for an m in there. That's arrow says what direction to rewrite in. I say, ooh, the n changes to an m. Both sides are equal. I'm back to my reflexivity and QED. Sometimes proofs are a little harder. So that here, you've seen that above, is Boolean equality of a natural number, which is not the same as this one, right? That equality is a proposition. That's a logical equality. Whereas that is a function that when it gets called returns a Boolean. It's two completely separate concepts here. I'm coming back to that in a moment, so bear with me for a moment. So I'm saying this is an expression that returns a Boolean, and that expression is equal to false. And you'd think that any n plus 1 equals 0 should be true, shouldn't it? We can try solving it like we had before. We use intros to pull up the n. Then we try simplification and bad, nothing happens. Okay, admitted, cancelled the proof. It says, okay, we cannot show that. Admit that. And try that again. Same theorem we want to show. Now this time, we're using a new tactic called destruct. We say here we know n is a natural number. So we have, in that inductive definition, exactly two ways of generating a natural number. Either it's 0 or it's a successor of some other thing. So we say we destruct the n and look at the two cases. We look at the case 0, and that's the non-existing parameter here between the opening bracket and the pipe that doesn't get a name because it's not there. And in the other case, we have successor of something, and that something gets the name n prime in here. So we see there are two subgoals we want to prove. And now that we can simplify and prove by reflexivity quite easily. So that's my first subgoal. We show that it's true for a 0 case. It is trivially. And we show that that is true, and we're done. Okay. Now for the fun part. Since we have inductive definitions, you probably already have figured that we're going to do inductive proofs as well. And that's what you do. That's where the fun starts. So again, we try to show something that's pretty obvious, n plus 0 equals n. Now, in the other case around that we had above, where we had 0 plus n, now it's scrolled out, okay. 0 plus n was easily simplified. N plus 0 isn't as easily simplified because it's not left recursive. So we try what we did before, and it doesn't simplify. Dang. Okay. We try the trick we learned before, destruction. We look at the two cases. Intros n, we destruct n. We have the case n equals 0. That's looking pretty good. We can simplify that and say reflexivity. But now we want to show that, and it simplifies, but we cannot really go on from there, can we? We have now, there's something missing. And the thing that is missing is called the induction hypothesis. And that's what we're going to do here. Fortunately, if we do an inductive type definition of some type in Coq, we'll automatically get a theorem that gives us the induction principle for that type. And that we can use using the tactic induction. Okay, intro again, this time the induction. 0 case as before, trivial. And now the second case, and we have an induction hypothesis, IH induction hypothesis for n prime. We simplify. We see we can use the induction hypothesis for rewriting our proof goal. Both sides are equal, and we win. Actually, we could have written the induction principle manually, and we could have proven it and then used it. Using check, we can have a look at what the induction hypothesis looks like. So it's for all propositions P, if there's a nut that generates a proposition, then if that proposition holds for 0, follows if the proposition holds for the successor, then it holds for all n. Okay, we're coming back to that in a moment, just for the people who know what it is and who are interested. One more thing we need in the type universe, before we get to propositions and the interesting stuff, is polymorphic types. Again, the Haskell folks probably know that. If you ever use C++ templates, you know that. You can construct, types are higher order objects, and you can construct new types from old types. So this is inductive definition in the regular style, like we've seen before, for a list of booleans. We want to save booleans in a list. We have two constructors, one we call nil, and that's a boolean list on itself. And we have another constructor called cons, which is a function that takes a boolean and a list of booleans, and then returns the new list of booleans. Yeah, obvious. We have the nil constructor, we have the cons constructor, and we can actually call the cons functions, passing booleans here, here, and here, till bool nil, to construct an instance of that list. All the list programmers know, cons, how to construct lists. And of course, it's pretty bad if you keep on constructing a list type for every type of data you want to put into lists. So you can parameterize your inductive definition. You can say, I have an inductive definition that gets an argument, x of type, and returns a type. And we can use that x as a bound variable in here in our definition. And then we see that nil actually is for all x of type, a list for that x. So if we pass that a type bool, then nil bool will produce this int nil for a boolean list, and a cons. The cons if you pass the type. So the type is passed around as an extra argument, and usually the type checker and the type inferencing makes sure you do not have to write it manually. Do not want to go into that into too much detail. Just so you have seen, we have polymorphic types. We can construct types. We can return types from functions. So check gives us a type. So if we check list, we see that list is a function that you give a type and that returns a type. And if you pass, as defined here, if you pass bool to that list, we end up with a set. So set is the type for all ordinary things like booleans, numbers, etc., etc. Of course, set itself also has a type. It is of type type. And type, again, is of type type. Well, not really. They're starting indexing them, type 0, type 1, type 2, just to avoid Zeno's paradoxon. You know, this sentence is false, recursive problems with, so they're using meta errors for types. So, of course, there's the interesting questions. Are there any other types except set? And the answer is yes, there is. And that's propositions. We've already seen propositions in our theorems. I've just used the equal sign and the propositions, figuring you see intuitively what's going on. We're now going to look into detail of how propositions work. And bear with me, because that's the second interesting part, because our dependent types consist of a type and a proposition. So types we have seen, now for propositions. 2 equals 2 is a proposition. That's a proposition. Here we see the difference between the two. So 2 equals 2 is a proposition. And BEQ nut of 2 and 2 is an expression of type bool. And the main difference is that that expression that belongs to the type set is computable, whereas a proposition must not necessarily be computable. It might be true, it might be false, it might be undecidable, and we can still work with it. That's the interesting thing, because that's where we can apply the mathematical power and show that our puny computable function that we wrote actually adheres to some higher idea of a non-total, interesting, incomplete function that's not provable. So what can we do with propositions? We can give them a name. You already have seen theorem definitions above. You can say 2 plus 2 equals 4 gets a name. And if we do that using a theorem, we implicitly say that theorem is true. So we are now asked for a proof to show that that proposition that we gave actually is true, which of course, as we have seen in that case, is easy. You can also give some proposition a name without showing that it's true or false by just using a definition. So we see that's a proposition. We could, for instance, put a 5 here. That's still a proposition. It's a false proposition, but we do not care at that point. Theorems are always true, and we have to show that. Such definitions are not. Now you will notice an interesting fact, and that is that there's not much difference between the way sets are used in functions and the way propositions are used. So in fact, the only thing is that instead of a type here, I've written prop. And that's because propositions are part of the same universe as the other types are. They're not necessarily concrete in that you can compute them in your running program, but while you're compiling, while you're doing proofs, they exist as in the context and as goals of your proofs. Okay, so here we have given a name to a proposition. We can also define a theorem, use that name here. We can define propositions that are obviously, oh yeah, that's no longer true, I changed my code. See, that's why you do that stuff. Now that definition above is no longer a true proposition, so I cannot prove it. Have to change that back to 4. And there we go. We can define weird propositions. We can say if 2 plus 2 equals 5, then follows that 99 plus 36 equals 42. Which, by the way, is a true statement. Ex falso quod libet. We can fall back to computation for defining a proposition. We can say that computable expression equals that Boolean value, which gives us a proposition for even. So even now is a function that returns a proposition. That's interesting. So I could say even of 4, and I then get a proposition that 4 is an even number, which is either false or true. In that case, we know it's true. It's essentially, you see the similarity to how functions work while programming. I've written essentially a function that takes a natural number, and I return a proposition instead of a value. And I can do that for 3, which of course means that it's a false proposition. I can define even more complex propositions. Say that if n is an even number, then so is the successor of n. I then can do funky stuff. I can write a definition that when you pass in a proposition that maps a function that takes a natural number and returns a proposition, then returns the proposition that p is true for 0. So it starts to boggle the mind when you think longer about it, and that's still one of the easy examples. So I have a p. My p might be even. I could take that even, which is a map from a natural number to a proposition, call true for 0 of even, and I get back the proposition that even is true for the value 0. All right, that's what I wrote there. Can come up with a definition preserved by a successor. So you take a proposition, an index proposition that maps a natural number to a proposition, and you get back the proposition that if for all n prime, if p is true for n prime, it is also true for the successor of n prime. Could be useful. We can write that a proposition is true for all numbers. So we say true for all numbers for all n, p of n. And then we can use that to define the induction principle for natural numbers. Isn't that fun? And much better readable than the other one that's auto-generated before. As you see, we're working with abstract things here. We're working with mathematic objects, not with real-world objects in your program that you're executing. And we are essentially using the same principles of engineering for constructing readable and maintainable proofs as we are doing for writing readable and maintainable code. So that's very, very interesting. We're going to see proof engineers soon, proof hackers, I hope. Okay, we've seen that sets, the day-to-day objects in your running code, are defined inductively. I have a very simple inductive definition for days here. I say Monday is a constructor for a day, Tuesday is Wednesday, Thursday, Friday, etc. And here I have an inductive definition for a proposition. I say there are 2 good days. I have 2 constructors for good day, one which I call GDSet, and that is of type good day Saturday. And I've constructed GDSun, which is of type good day Sunday. You can look at it from a different angle. You can say, I know the proposition is true if you give me evidence that the proposition is true. And there are inductively 2 possible ways to give me an evidence that a day is good. One is that you show me it's a Saturday, and the other one is that you show me the day is a Sunday. Let that sink in for a bit. Inductive definitions of proposition, extremely useful. I then can say, I then can use these constructors for the inductive type in proofs. Say, I want to prove that Sunday is a good day, that the proposition good day Sunday, that you get by applying a piece of data to the good day constructor here, that Sunday is actually a good day, that that proposition is true. So again, we want to do a proof. We are then using apply of that constructor, which funnily is exactly the same as applying a function would be. I'm getting to that. And QED. So we can use, we can prove that Sunday is a good day by saying, yeah, look for that constructor. That's the right one. Let me check where to explain that. Oh yeah, we're about there. A couple of more fun things for propositions. You can do more complex things here, like, every day is a fine day for singing, so we can say that. We can have an inductive definition that every day is fine for singing by providing a single constructor with a for all D day, it's a fine day for singing. And again, we can show that Wednesday is a fine day for singing by saying, yeah, apply the constructor and QED. Now, there's an interesting thing here. You might have noticed that it all looks very familiar, no matter whether we're writing programs, we talk about data and functions, or whether we are talking about the world of propositions, where we talk about propositions or theorems, or however you want to call them, and evidence that something is the case, or as other people call it, a proof. And there's a very important principle, the so-called Curry-Howard isomorphism, which that whole stuff is built upon. And the Curry-Howard isomorphism essentially says that if you have a lambda calculus, a type lambda calculus, you have expressions and you have types of expressions. And expressions relate to type of expressions exactly as proofs relate to the propositions that you prove. It's 100% identical. You can use lambda calculus to do any mathematical proof by writing your proposition essentially as a type for the lambda calculus, and then constructing the right object out of inductive definitions that fulfills that definition. And actually, the thing we've seen using the proof and the different tacticals, that's all just helper functions that help me construct proof objects. And we can see that here. I can give an alternative definition. I can take the FDFS any constructor and pass a Wednesday object to it, an instance of a Wednesday. And what I end up with is a proof object that shows me that Wednesday is a fine day for singing, right? This here is, that name is bound to that expression, and it has this type. Just that that expression is a proof, and that type is a proposition we're trying to prove. Did everybody get that? Good. Isn't that awesome? Okay, we can look at that. So we have a direct definition of a proof object here. And you see they both show that Wednesday is a fine day for singing. Okay, another inductive definition. By now you should have gotten the hang of inductive definitions. We have an inductive definition of the day before. We say it's 7 ways to construct a day before some other day. That's all of them. And we say an okay day here, also inductively defined. And we know if it's a good day, so all days for all days. If it's a good day, we know it's an okay day. But if we have a day 1 and a day 2, if day 2 is an okay day and D1 is the day before D2, then D1 is also okay. It's sort of a contrived example because it means that all days are okay. I have my doubts about Mondays. But it allows us to show you how those proof objects can be nested. See that here? The first one is, let's make it like that. Let's execute that until here. We can actually call all the constructors directly to come up with an object. So we want, the type of that expression is okay day Wednesday. So that expression is a proof that Wednesday is an okay day. And we start out with there. We know that Saturday is a good day. And so we know that it's an okay day because we have the okay day, good day constructor. It's actually functions where we pass other proofs as arguments, which are then constructors, etc., etc. And that's the whole statement we're having here. That's the raw proof object. Of course, nobody in his sane mind writes that manually, but it works. We then can, I'm going to show that step by step, using tactics to give that proof. We say, okay, here's a proof goal. We want to show that Wednesday is an okay day. So we know that it's the day before Thursday, so we can use the okay day before constructor, where D2 is a Thursday. So now we have to show that the day before Thursday is Wednesday as a sub-goal, and we have to show that Thursday is an okay day. Which of course we do by saying that, yeah, Friday is the day before Thursday, another sub-goal to prove, and Friday is an okay day because it comes after Saturday. Now we have 4 sub-goals to prove, and we have to show that Saturday is an okay day. And we know that because we know it's a good day. Yeah, only 3 sub-goals left. So we know Friday is the day before Saturday by constructor, we know that by constructor, we know that by constructor, and whoo, proof completed. We've shown that Wednesday is an okay day. Of course, you do not want to do that manually either, and that's where proof automation comes into play. If you are into the formal verification scene, you might have heard about stuff like SMT solvers. That essentially try to automatically prove certain theorems. Those things are fine for certain subsets of problems where you can show that your algorithm for automatically finding the proof terminates. In Coq, you can handle stuff where you cannot show that your general algorithm terminates. But you can, of course, if you have some manual solving, some subset of a problem that you can solve with something SMT, you can directly call that as a function. So the next thing we say is that the automatic stuff should please look at the constructors of the day before, and then we can essentially repeat the same thing again and again. Here's again a proof goal. We say for the second argument, that's the Wednesday, use the extended constructor and solve the rest automatically. Do that again, and do that again, until we are at Saturday. And then we say use the constructor 1, use the constructor again, and again the proof is completed. You can get even more fancy by scripting that a bit. That essentially says, semicolon says, try that tactic to all results of the tactic before. Try says, if it works, it works. If it doesn't work, leave me the rest of the sub-goals. Repeat says, do that as often as possible until it's solved, and or is what you would imagine if the left side doesn't solve anything anymore, the right side does. So that one-liner now solves us the complete problem. And that very same proof also would show that Tuesday is a good day. Whoops. Yes. No, please give me the other keyboard layer. Thank you. Tuesday. Proof completed. Which of course is very nice. Once you start hacking your code, you might change your code, and if you have brittle proofs, then you have to redo the proofs again and again. If you look into the principles behind it and start automating your proofs and writing little scripts for your proofs, you tend up ending up with a much more flexible system. So, but the point here is that all of those 4 ways to come up with a proof generate the very same proof object. And if you look at it even in the notation, you see, here's the name, that's the value, and here's the type. And due to the Curry-Howard isomorphism, that's the proposition we're showing. That's our proof in form of the proof object, and that's the name of the proof, which we then can use in other proofs in form of apply. Okay, so much for propositions. Bear with me for another excursion until we finally put all of that together and I show you a real-world example of certified programming with dependent types, even if it's trivial. But the whole goal of the talk is explaining to you what the title of the talk actually means. When we want to do proofs, we of course want to have the whole universe of propositional logic that we know, like implication, existential quantifier, universal quantifier, logical conjunction, logical disjunction. And it's actually possible, as we constructed Booleans from scratch and as we constructed integers from scratch, to construct almost all of that from scratch as well. The only thing that's actually built in is the for all universal quantifier, and that happens to be equivalent to a lambda expression, to defining an argument for a function. So for all n introduces a variable n in the scope of the expression behind it, which is totally equivalent to if you define a function f of n, which again is equivalent to lambda n dot use n for something. So for all is equivalent to lambda, and that's part of lambda calculus. The first thing we see is that implication is essentially a subset of universal quantification. If we quantify over an expression where we do not reference the value we have introduced, the e, if e is not free in that expression here, we can, we'll either not give it a name at all, write an underscore, that means I do not care, or use a bit of syntactic sugar, which is this arrow, and it's defined like the other syntactic sugar we've seen. I've shown you the notation that changes the grammar of the language. That arrow is implemented as the same and actually expands on a syntactical level to a for all definition, which in turn is the same as lambda calculus. So we have universal quantification built in from lambda calculus. We have implication as being equivalent. And again, you see here, it's even printed the same because it's internally the same. We can define AND as an inductive proposition that takes two parameters, p and q. And yeah, it has one constructor that says if p is true, then if q is true, then the expression AND pq is true. Obvious, we use implication to define AND. We can introduce a notation for that. We can then say, give a definition for if and only if, and that's from p follows q and from q follows p. Put a notation for that. We can introduce logical OR by saying there's two ways to provide evidence that an expression OR pq is true. That is by either coming up with a proof for p and then knowing that OR pq is true, or we come up with a proof for q and then we know that OR pq is true. Notation for that. And then even equality. You know, I've used that equal sign in propositions right when I showed you the first proof. And it turns out that that isn't built in either. All that's built in is for all. And equality is actually defined like that. I copied that straight from boot up source. It says there's one constructor. If I pass it in x, then I know that x is equal to x for all types large X. And there's a notation that introduces the equality. So the equality is not even a symbol in the base grammar. It's all defined in the startup. So now we're coming for the good stuff. Putting it all together, dependent types. As you might have guessed by now, that's also not really built into the language. It's constructed as an inductive data type like everything else. And the interesting thing is that it's exactly what I explained in the TLDR at the beginning. we define a sig, inductively a sigma type that is getting in a type A and a proposition P that maps instances of that type to a proposition. And that is a type definition. And all members of the type are those X of type A where P of X holds true. So it follows that sig of P is true. We have a funny notation for that as well. That's probably familiar if you're using math. It's in curly brackets. I have an X of type A for which P holds. That's a dependent type. I can run that till here. Then we see, if you check that expression, we see, no, that's a set. And now the putting it all together part, as I said, a very, very simple example. We've seen before a definition for a proposition that says a number is even. That falls back to computation, to the even b function that we defined before. It's also, of course, possible to inductively define the even proposition. That's what we're doing here. We say there's two ways to provide evidence that a number is even, and that we do by either saying it's a zero is even, or if we pass it a proof that n is even, we get back a proof that the successor of n is even. Okay? So now we can put that all together, use the sigma type, and say even number now is a type that consists of all x that are natural numbers for which that proposition is true, for which x is even. So I can now write function that return even number. That's again a definition. No arguments here. The type is even number. So I'm saying here, whatever you're getting back there is not only a number, it is even. And I construct the return value, which is a sigma type, by calling the exist constructor that I just defined up there. See, they exist here. Just call that. Need to give an underscore here because it's a type, long story, blah, blah, and type checker needs it. Then I say, here's my 0, that's a number, and here is my proof that what I return is 0, which is essentially just a proof object consisting of ev underscore 0. And that works. I've successfully constructed, can say, check, return even number. And then now I will get back an even number there. I know in that case it's 0. Okay, now you say manual constructing proof objects everywhere in your code might get messy. There's another trick, and that's the program definition keyword. I again do the same. I want to return a 0. The exist is boilerplate for saying I return a dependent type or restricted type. That underscore again is the type of the underlying type, which is not. And now that underscore is the proof. If I go here with execution, I see I have a definition, but it says I have obligations. There are certain things the proof assistant cannot find out on its own. And I can now use tactics to construct the proof object that I would have had to construct manually here. So I say, as we've seen before, by constructor you see, that's correct. Okay, I put the constructor hints in my database because then, so I essentially say here, if you're trying to automatically solve my obligations, please have a look at the constructors of EV because that might help you. And if I do that definition, and it will find the proof automatically for me. So once you start using that, you have to start passing around proofs that what you return is actually an even number. And that can be made easier using those automation tricks. Here's another instance of a function. This time, I'm passing in an even number, and I'm returning an even number. And I add 2 to the number I pass. We've seen the match before. I match on the even number, and I destruct it using the exist constructor. I'm getting back my x here, and I'm getting back a proposition h, which is the hypothesis that this is an even number, which I now can use to construct another proof that the successor of the successor is an even number, that I'm doing here. So I'm using the EVSS constructor, passing that number again, passing the hypothesis here that I extracted from there, and I'm returning my 2 plus x, again in an exist statement. And it works. So if you want to call that function, you have to come up with a proof that the x you're passing is even. And I'm using that here to prove that what I return is even as well. Again, we can do the same thing using program definition, which makes a couple of things easier for me. For one, it automatically destructs the dependently typed argument. And the other one is, instead of manually constructing the proof object in my code, I write an underscore, and after I'm done with my code, so again, it's pretty obvious what's going on here. Like I'm adding 2 to the argument, returning that. I'm saying I'm getting in even number, I'm passing out an even number, and I probably need some kind of proof to show that. So that's what I'm going to do here. I have to show that if xe is an even number, that this expression, which is the expansion of this expression, is an even number. And I can do that like that. Proof is completed. If I have similar cases, I can also completely automate obligation finding again by, that's an old programming language for tactics. You can write your own tactics. I'm not going into detail what that does. But as soon as I do, you see, it will find my proof automatically. And I can write a different function and reuse the same tactical definition. And it will still find the proof automatically. Now, the interesting thing is that that whole passing around of proofs is something that completely vanishes once you extract that to ML code. So that's what's actually extracted from out of there. You see that's the compiler inlines that too for the OCaml compiler. But I'm no longer passing around the proofs here. That's just the computation. And all the passing of proofs is just there for me. So I'm able to convince the proof automation system, the type checker, that what I say about it is actually true. So what is that good for? Why would you want to have that? And the answer is because it allows you to specify the behavior of your program. You can say, for instance, if you implement sorting of a list, you can come up with an inductive definition of a proposition. What does it mean for a list to be sorted? You can then implement your sorting function. You no longer say, my type is list arrow list. You say your type is list arrow sorted list. And then you won't be able to compile that until you show proof that your code has the right type. So you can use it to strengthen the type of functions up to a point where the complete specification for the function is in the type. And you will have the type checker check for you that this is correct. So that's for the result value. You can also use it on the other side of a function. If you have something that's brittle, you say you have a precondition. You can specify the precondition as a proposition, as a dependent type in the argument. And yeah, if a user wants to call your function, he can only do that if he comes up with a proof that he will always pass the right value to you. Like the applications for that are endless. Say you access a buffer, you could either check the bounds every time, or you could write a function where you say, I'm being passed a list of length L and an index I, and I is smaller than the length of L. And then it's up to the caller to show that he will never pass you a wrong index. So either you have bounds check or you come up with the proof that the bound will be checked, which means you can write code that's very, very efficient and still keep your requirements under control by secure code. We have, and that's where I'm done with my talk, and I'm opening the mic for questions in a second. Together with Marco, we have written a PDF parser with a goal to separate good PDFs from malware PDFs, because that's a big problem. And we've used COC mostly because we could, not because it's the most efficient, but we got very interesting results. What we essentially do is parse it. Then if there's any JavaScript in it, we reject it. If it's not a standards compliant PDF, we reject it too. And that already gave us a 95% match rate for good PDFs and a 95% rejection rate for bogus PDFs. So a very, very good, like 5 lines of rules of what's good, what's not good, filter for malware PDFs. And yeah, we used the stuff I've showed you, the dependent types, to show termination of the parser. By, first by defining a proposition that says, what's the sublist? So when you have a parser, why should a parser terminate? Especially if you have a clean star where you say, I call the parser until I run out of string. That's a recursive call. How do you show it terminates? We do that by saying that a parser, here's a parser definition. A parser is a type constructor where you pass a type. And what you get back is something that when you have a list, you'll get back a type T, which is the parse object type, and a sublist, or the tail of the other list. So we say a parser is not just a function that returns like an integer and a rest of tokens. We say it returns an integer and the rest of tokens, where the rest of tokens is a true tail of the list we originally put in, because that allows us to show that the recursion terminates. That's what we do here. So parser combinator many, using many helper function. We pass a parser for type T and a ASCII list or a string. And we have here a recursive call to the many helper function. Here's the recursive call to the many helper function, where we call our parser function on the tokens as long as there are tokens. And then here we give the proof that that stuff terminates, because our sublist has a measure which is well formed and according to the rules terminates. Okay, we would have loved to come up with a more formal parser for PDF. Unfortunately, the specification is so badly written that PDF has no formal specification. So we couldn't do any of the fancy show that our parser is equivalent to the formal specification of PDF thing, because there is none. But at least we know that our PDF parser will terminate. Since it's compiled to OCaml, we know it has no buffer overflows. It has, oh yeah, we do a trick. We catch overflows and terminate. We might run out of stack and then terminate, but at least we know that we add no additional memory corruption vulnerabilities in that thing. So we improve the security very costly by filtering out 95% of the bad stuff, without adding additional vulnerabilities to the system. So that's why we did it. Okay, I think I'm over. Mike is up for questions.
So if you have any question, please line up after the mic in the middle.
So once you have a proven
A little bit louder, please.
Well, once you have a proven PDF parser in OCaml, how do you deliver that to anyone? Because most of us are not going to be writing web applications in OCaml to make use of this library.
Well, I do what everybody else does. I extract OCaml code out of my COC, and I compile that using the OCaml compiler, and I have a binary, and I ship that.
So you export a C binary?
No,
A
not a
C
C
library.
binary. There's no C involved.
Well, so if I wanted to use the PDF parser from Ruby, the same way I can use a C PDF parser.
Wait, what?
If I wanted to use the PDF parser from Ruby, the same way I can use a C PDF parser.
Well, there could be ways, but frankly, I haven't thought much about it because, yeah, I wanted to start with something that works and not think about how to attach it to a different language because adaptation problems are big. And as soon as I have other languages in there that are not part of that formal system, I'm losing the property of my formal system. So who's telling me that Ruby doesn't have bugs that corrupt my memory?
Well, no one's telling you that.
Exactly, that's the reason.
Right. But that's really neither here nor there because it's of little value to produce a library in a language that no one can practically bind to.
Well,
or to say,
well,
if you allow binding.
It might be of little use to you for your special application, but if I run it as a standalone executable on a web firewall on a mail server for, say, a large corporation, and it catches me 95% of all spear phishing mails, it is useful.
Okay, I grant that.
Yeah, okay. I have a few questions concerning the practicality of the whole thing. So can you talk a bit about the overhead of doing that, how difficult it is to change stuff after you've specified stuff, and also about the quality of the code? I mean, if I do everything with successors, that's definitely slow, right?
Yeah, let me pull up the real code to show you what we do there. Lots of code. Yeah. There we go. We're cheating. We model our natural numbers. I use that imports, and that essentially map natural numbers to OCaml natural numbers. Oh. So they're not actually represented in the successor of X form. They are inside your proof assistant. As long as you're in that interactive mode where you write your code or write your proofs, it actually builds up huge heap structures. If you want to represent a number 30,000, it allocates 30,000 heap cells. So it's pretty inefficient. But during code extraction process, you can map that to real-world data types that perform a little better. There are crooks to that. I'm not completely happy yet with that. But it can be made to work. It's not for the faint of heart because you might have to pull compiler tricks inside the OCaml compiler or mess with the code extraction part of that.
Do you get into troubles with overflows? I mean, I don't know OCaml good enough. Does the int have like a max value and stuff like that?
A what?
A maximum value and stuff like that, or is it a big int?
It does. Now it's getting ugly. You're asking the good questions.
Yeah.
Let me show you the make file.
Oh dear.
Do you see that line?
Yes, I do.
If the integer overflows, I get an exception. And
Okay.
there's some top-level code. Where's my top-level code? There's a top-level code. Do I handle the error somewhere? So that's actually the ML code. I've said COC is complete. It's also completely functional. So for reading data from a file and writing it back, I actually have to write some ML code manually. And yeah, I'm just getting an exception there that is not caught, and it will not say it's a good PDF if an integer overflows. So,
Okay.
of course, it would be better if I had a target language that would support big nums in an efficient way. But
Given the
that's a
state of
trick I
things.
do.
Okay. Okay, and how hard is it to work with this stuff, to refactor it if you have changes? What is the overhead of doing all that?
It's sometimes surprisingly hard. So the first thing that was harder than I thought was printing numbers. You'd say printing numbers is easy. It just happens that, here is it. How do you print a number? You divide it by 10, look at the result of the division and at the rest. The rest is your digit, and if the result is above 0, you do it recursively. Yeah, you do it recursively. That's the trick. It allows you to do recursive calls when you show that that recursion will eventually terminate, which in that case breaks down to you have to show that n is larger than n divided by 10. I played around with that for about 4 hours until I found a standard library proof, which is that one that I can use for showing that. So you run into situations where you think, oh, that's easy, I do a recursion here, and then you spend some hours proving that you actually are allowed to do that recursion. And the same is for other proofs. So you run into interesting problems. I wouldn't say it's easier than regularly writing code, but it does catch bugs. So the other thing where we needed to do something interesting is cross-ref table parsing in PDF files. I show you the test file we generated. Now, stupid Emacs. You're not supposed to parse that file. Let me try that again. Yeah, that's better. Okay. If you've ever looked at the PDF, you see that at the end there's that xref section. And what that is it's giving objects offsets in the file. So from that I know that object number 1 has byte offset 1058, object number 2 is 1141, 1216, etc., etc. And PDF is an incremental file format, which means you can just add data to the end, and then you have a trailer dictionary. In the trailer dictionary, you say pref, and that's the byte offset of the previous xref table, which is here. So the naive way of implementing that is, of course, recursively, right? You parse the table. Once you're done table, you recursively call yourself using the other offset. No. Can you see it already? Who sees the problem already? 1, 2? Mutual recursion, right? If in your second xref table you have a pref that points back to the first xref table, guess what happens? I can show you what happens. At least what happens in GNOME.
Oh dear.
Gets better. Okay, so what we do now is keeping a list of offsets we've already seen. And then we have a proof that this will finally terminate because at some time we will have seen all offsets in the file, which is a finite set. I can scroll through the proof for that for you. Where's that? Yeah, that. That was quite a bit of work. That's nasty. That took us 6 weeks to write. But now we have proof that we will not have that bug in our code.
Thank you.
Hi, I've just a short question. Is it possible to prove that there are no integer overflows? So, I mean, you map a natural number, which can be as large as infinitely large, and you map it to a 32-bit integer, and the compiled program crashes at runtime. But can't you prove that there are no numbers too large in your program?
Yes, it will get a bit messy. It's not the approach I would use for a production system. The real approach is to define the semantics for a language that has no overflow, that has big nums, and then show that your machine words, your implementation of that big num using machine words is correct. But of course you could use that, which buffer was it? That buffer. You could write something like that. Where have they gone? There. With whatever.
Okay, so it's possible, but it's not practical.
It's possible, but it's not the approach I would be using.
Okay, thank you.
Yeah.
Could you use this approach to prove stuff? Use to prove runtime properties of a program, like saying this algorithm always terminates within 1,000 cycles of CPU?
In theory, yes, because we have the lambda calculus and the calculus of inductive constructions, and we can use that to represent the whole of the mathematical universe, which does include complexity analysis. And people actually do that. They work on metrics for programming languages. You'd probably also want to be able to say that that function has a complexity of O of n times log n, something like that. People are working on that. It's not production ready yet.
So are there any questions from flow control?
There is a remark for the guy who asked about support for OCaml in Ruby. OCaml has a C calling interface which can be attached to Ruby somehow.
Okay. Yeah, I can see that you could make it work, but I frankly wouldn't want to write all that interfacing stuff, etc., etc. It's a mess. Okay.
What about the complexity of your basic operations, like addition based on size of a natural number? Like, is it a constant time or linear time with carry between machine words?
I go back here to the extraction code. We see that I say, please implement the division function in Coq by using the slash operator in OCaml. So essentially, I'm cheating here a bit because nobody's telling me that the function I'm calling in my extracted code does exactly what I'm doing here. So if you want to have like real proof that it works, you'd need to show that this is a correct implementation according to the specification. So of course it sounds like if you implement addition recursively and then multiplication recursively on top of addition, and you have your numbers where you count by calling successor functions, of course it's painfully slow and not constant in real time. And of course, you need to, at the end, use primitives. And part of the unsolved challenge, which people are working on, by the way, is having that part proven as well. So that from that you say you have a machine function with the semantics of X, and that this is equivalent to your definition in Coq.
Okay, one more question.
Yeah, conceptual question, kind of like, you talked about the halting problem.
Yeah.
And what would you say is the relation between Coq and the halting problem? Are you trying to avoid the problems inherent in the like halting problematic, or do you like, what is this relation? Are you trying to avoid it, or?
Yes, of course you want to avoid running into the halting problem. But it's more like, you know, like NP-complete problems. We know NP-complete problems are hard, but there are good heuristics for that, for most of them. And it's a little bit like that here. So coming up with a general scheme to prove certain things is equivalent to the halting problem. But still, since we are writing parts of the proof manually, we can sort of find our way through the design space and see whether we can find a solution that works. Even though in the general case it wouldn't work, we might have a special case that we are able to make work manually. So we are moving towards the territory of the halting problem, but only as far as we can get.
Okay, thank you, Andreas, for giving back some hope. You guys, please take out some trash and have a good night.
Yeah.